So good afternoon. Today's department seminar will be given by Ziga Brencic. So Ziga has obtained his diploma at Faculty of Mathematics and Physics here in Ljubljana. Afterwards, he was at students exchange at ETH Zurich. So his master thesis was on determination of working channels in the air reach of the Bell spectrometer. Since 2020, he has PhD at our department, and he is working on effects of electric fields and ion gas collisions on ion dynamics in time of flight mass spectrometry. So therefore is a part of SuperFRS collaboration. Ziga will tell us today a bit about exotic isotopes and exotic bound states. So we are looking forward to this exotic nuclear physics. So Ziga, please.
All right, thanks, Jelena, for the introduction. On Zoom, you can hear me well. Maybe write to the chat so we know you're okay. No complaints, I guess. All right. So thanks, Jelena, for the introduction. So the stuff I'm going to talk about today isn't directly part of my PhD topic, but it's basically sort of the backbone of the, let's say, nuclear physics we currently do. And I'll try to represent some of the stuff that is currently sort of a hot topic in nuclear physics, more like exotic processes that you might have not heard about in the normal courses. And I mean, not exotic as, you know, decaying raspberries, because they don't exist, but exotic in another way. So this talk was actually created for the seminar I had in Germany under the supervision of Christoph Scheidberger. He's a head of SuperFRS in Germany. And like under his supervision, this is what I produced. So, and of course, this doesn't work. All right, I guess I'm gonna have, okay. So let's start with, let's say, a bit of history. As you might know, in quite a while ago, Mendeleev figured that all the elements we know have to be somehow ordered. And he came up with the periodic system, and at the time, we actually knew about 66 elements. A few years later, the periodic system looks like this. We have around 118 elements. But the interesting part is that when the chemists created the periodic table, they didn't really know about protons and neutrons and the structure of the nucleus, but they already ordered, let's say, elements we have in nature according to proton number. And and then, of course, after that, what was observed that in specific, let's say, parts of the periodic table, stuff started to pop up that was sort of chemically and based on the number of protons belonging to the same place, but wasn't exactly the same, because later on it turned out that it had different number of neutrons. And it's actually quite a funny story that isotope literally means at the same place. So they kind of said, okay, it belongs to the same place in the periodic table. But this popping up of new states and all the different phenomena, then later on resulted that the nuclear physicists like Fermi and Sergey were trying to figure out how to order all of this. And in 1934, they actually came up with the first idea for the nuclear chart. And then in 1946, Emilio Sergey with his wife actually created the first nuclear chart. And this is actually how it looked like. And of course, now in laboratories, we have something more fancy. But the interesting part about this story is that here there was around 46 isotopes known or something like that. And historically, over the years, the amount of known isotopes has grown significantly. And as of today, we have quite a lot of them. But it turns out that the story is not complete. And at the moment, yes, we know 270 stable nuclei with masses up to 118. And we actually measured so far 3,000 isotopes, which is a lot, but it actually turns out that it's not everything that should exist. According to theoretical models, there should be around 7,800 isotopes. And on this chart, we can actually see that this is the stuff we so far observed. And this is the stuff that should exist. So this color coding is sort of like, what is the probability that this isotope should exist in nature and that we should be able to measure it? And if you check this, you can see that, well, we have a lot of work to do. Now, of course, the obvious question is, okay, so we just have to do more sample collection and we're done. But not quite, because it actually turns out that as we go away from the stability line, the thing we were taught about in nuclear physics courses, funny things start to happen. So in the rest of the seminar, we'll look at some of this interesting phenomena and why we actually just don't want to measure masses of isotopes and their properties, but also figure out if there's any new nuclear physics around those regions at the limits of the existence. So to jog your memory a little bit, of course, in nucleus, it turns out that it's better for the nucleus to be bounded. So it's the mass of the bounded constituents is sort of smaller than all of them separately. And the difference is basically the binding energy. And we're going to define in this talk normal nuclei as sort of the ones that are described well by the liquid drop model. So the nuclei around the stability line. And we're also going to say that if the particle shell model with Woods-Saxon potential sort of describes them fine, they're sort of normal nuclei. We're not going to need this for the exotic definition. It's a bit, let's say, weird definition, but it does the job well. So, as I said, the exotic nuclei are everything that has weird properties in terms of mass, size, shape, half-lives, and the electric and magnetic moments. So if the simple stuff you learned in introductory nuclear physics courses doesn't describe them, they're doing something funny. So in the nuclear chart itself, there are several regions where this exotic stuff is, let's say, most pronounced or most interesting. And the one part is so-called island of stability, which is at very, very heavy isotopes. And here it's predicted that here we should have a lot of stable states, but not many of them have been yet observed. Then here is the so-called region of end of the value of stability. So basically this is the end of where we know the stable isotopes in nature. And there's this region called terra incognita. We're not going to dive deep into it because it can be a whole talk in itself, like basically every slide. But basically, this is one of the, let's say, frontiers where the accelerators are trying to go. Then there are two lines called neutron and proton drip line, which are basically the limits of the existence of the nuclei where they should be. And then there's this n equals that line, which is of interest because it shows that if you look through a nuclear chart, as you might remember from introductory courses, is that nuclear chart sort of like curves. So the stable isotopes sort of curve and have more neutrons than actually protons. And of course, the reason why this is because the repulsion between protons and the nucleus is different than the sort of attractive potential between the neutrons. And another region of interest, which is actually quite rich with exotic features, is sort of in here. So if we zoom in, what do we see in this region, and we'll look at some of this phenomena a little bit closer later on, is that it has been observed that in some isotopes, the isotope doesn't really behave like a nucleus, but it's formed out of clusters. And then in some cases, we get something like called proton halo. We'll look into this in a second. The neutron halo, we'll also look into this. And we have so-called neutron skin. So this basically means that the isotope that has a lot of neutrons sort of gets them around and it's sort of like covered with them on the surrounding area. And we can have significant deformations in some areas of the chart. We can get so-called bubble nuclei. So basically it means that at the center, there's like lower density for example, for protons. And as it turns out, magic numbers, as predicted by the shell model, sometimes disappear or extra appear. Now, the first, of course, question is, all right, so how do we get into every region of sort of the nuclear chart? And of course, we use accelerators and nuclear reactions. We're not going to go into details of this because, again, it can get a whole talk. But the important thing is that we can pretty much reach the whole nuclear chart, or most of it, with those three reactions. And there's also a fourth one process, which is currently sort of under studies and the development, which is so-called multi-nucleon transferred reactions. And with those, we hope to, let's say, reach also the regions that are here, not covered. Okay, so let's start with the first sort of exotic property. So nuclear radius should be, let's say, proportional to 1/3 of A, so the sum of neutrons and protons. And this works pretty well for nuclei above, let's say, A20, but it actually turns out that this is valid only around the stability line. And if you look closely at this chart here, you're going to notice that for same number of protons, if you keep adding neutrons, the radius starts to increase. So why? What is going on? So this is basically can be explained nicely with this simple picture. So let's say we start with helium-3 and we add a neutron and we have a bound state. We add another neutron and we have a state that it's not bound. So this neutron sort of doesn't couple with the rest. But then we add another neutron and we get 2 neutrons circling around the core. And we got a drastic radius enhancement, and this is what we call the so-called halo nucleus. And this is why when we actually go into the lab and measure, we're going to actually see a much larger radius. Then, if we add another neutron, we again don't get anything, so an unbound state. And if we add an extra neutron, we again get a halo, which has a larger radius, and it's also longer lived than, let's say, some of its lighter isotopes. And basically what the discovery of halos is how the exotic field was born. Now, of course, there's another story, which is a bit political and propaganda. And that is that after the World War II and Chernobyl, radioactivity wasn't the most popular word. So they kind of had to figure out, all right, we still want to do radioactive physics, but let's invent a new word. And they came up with exotics. So exotics are still radioactive, just we don't call them like that. Okay, so what's the big deal with halo nuclei, right? So let's say if we take lithium-11, which has 2 neutrons circling around the core, if we look at the radius of the first neutron, it turns out that the radius is similar to the calcium-48, which is significantly heavier. And if you look at the whole bound state, you actually see that the radius is pretty much like of the lead. So this discrepancy and why this starts to appear throughout the nuclear chart sort of gives us new states through which we get a new insight into how nuclear force actually behaves. Here are 2 more examples. So here's, for example, beryllium-11, and this is lithium-11 as we said before. So lithium-11 was actually the first halo nucleus that was discovered in 1987. Of course, when they were measuring this, they first thought they made a huge error in the measurement, but then it turned out it wasn't an error, but actually in physics. But I guess this is how it always starts. So we can also have 1 proton halos. So this basically means that around the nuclear core, a proton circles around, but this is disfavored because protons have repulsive interaction, and this is, let's say, not as favorable. So the next thing is, as I showed before, we can actually have halos with more than just 1 neutron or proton circling around, but multiple ones. We'll see later on which kind of, let's say, many body states we've observed so far. And most of halos so far that has been observed are in the neutron reach region, because as I said, in the proton side, they're disfavored. And another thing that is sort of interesting is so far in the lab, we have been able to produce only halos up to, let's say, mass around 28. Above that, they are predicted, but not yet observed, because it's really hard to get basically to the edge of the nuclear landscape where they actually appeared. One example theoretically predicted is calcium-72 and then helium-30. So here is a little bit of overview where they have been observed so far. So-called 4 neutron, 2 neutron, 1 neutron, 1 proton halo, and also the years of observation. I guess you can't see probably, but the years are pretty much after 70 onwards. And of course, this part of the chart is pretty easy in some sense to reach, but the higher we go, getting to the edge becomes a problem because we don't have the machines that are capable of this, but in principle, in the upcoming years, we should be able to also reach those regions. So one of the things, how let's say we measure that we actually have a halo is that you take you create a nuclear reaction, and in it you, let's say, produce lithium-11. And now you have your lithium-11, or let's take maybe this one, because it has just one neutron in the orbital, and it's going to be easier. And then you basically smash the projectile on the target. And if you now look at the actual frame of the projectile, you sort of knock out the neutron that is circling around. And then, because the reaction the process is fairly fast, you can then at the end measure the momentum of this final core that basically flies forward. And what happens, this is simply, let's say, a consequence of Heisenberg uncertainty principle, is that based on the momentum distribution of this final product that you measure, if it's very sharp, then the distribution in the nucleus had to be very broad. So it had to have sort of enhancement. And if the distribution in the momentum is very, very broad, then the reverse position, or basically the radius distribution, had to be very sharp. And this can be actually clearly seen in carbon, for example, that as you sort of go neutron more rich, so if you add neutrons, you basically, here it's see nicely that you start sort of with fairly broad momentum distribution, and then as the halo becomes more prominent, the momentum distribution sort of shrinks. Then the next thing, which sort of has to be mentioned here, is the process through which you measure this is basically, you want to measure what the radius is, right? And for this, you can use 3 types of cross sections. And in principle, what we use most is the so-called charge shading cross section. So either the proton one or the neutron cross section. And from those two, you can actually directly estimate what is the radius of the protons in the nucleus and the neutrons in the nucleus. Of course, the whole measurement is a little bit more complicated, but I don't want to go into details. So as was actually observed, is that in principle, by the model, simple model, we would expect that the radius goes like this. And for example, for this element, it goes nicely, but then for beryllium, for high mass numbers, so this is for the cases where we have large neutron excess, the radius starts to jump. And those are actually measurements. And also you can see from the cross section that the scattering in some sense on the proton part doesn't really change as you add neutrons, but the part for the scattering sort of on the neutron part of the nucleus sort of drastically increases as we go to actual halo. So this can be visualized in, let's say, another way. So in some sense, the density for the neutrons will sort of extend much further out. And also if we look at the root mean square radius, so basically the second momentum of the density distribution, we also see that the neutrons are more stretched out, and this can be nicely experimentally confirmed. So the next interesting thing, which I'm not going to go into detail because I think we have 2 experts in the audience for this, but basically what happens is that we can actually have so-called clustered formation in the nucleus itself. And the interesting part is that this phenomena is not just in carbon-12, but it can actually appear in other cases. So basically when we have specific kind of excitation energy, the nucleus starts to behave like it has specific kind of structure. Then another thing that is going to now get important as we go, let's say, close to the drip line, is that if you remember from your, let's say, introductory course, is that in the nucleus itself, we have the repulsive Coulomb force, then we have the attractive nuclear potential, and then if we combine those 2 parts, we sort of get something like this. And this is what the protons feel, and the neutrons in principle feel something like this. But as you actually get to heavier nuclei, what starts to happen, basically because of quantum mechanics and Pauli exclusion principle, is that we also get a prominent LS term. So this part, which actually results that even for the neutrons above, let's say, 0, you get sort of kind of barrier. And the reason why this is important is that at this point, as we're going to see later, is already the point where in order to steal a neutron or a proton from the nucleus itself, the separation energy is zero, but there's still potential barrier. And this can actually cause that we still get bound states pretty far out of the line of stability. We're going to take a closer look later. And because of the tunneling probability, we can get a state that it's sort of bound for some amount of time. Okay, so as a result, because radius changes and let's say wave functions change, etc., in some areas of the nuclear chart, we actually observe the so-called disappearance of magic numbers. So this is called pulsar shell quenching. And of course, in some cases, we get new magic numbers, which by the shell models shouldn't be there. And of course, all those kind of measurements, or let's say all this kind of phenomena, can be directly confirmed if we go to the, let's say, limits of the nuclear chart, measure the masses there, and then from there we can infer where different properties start to happen. So basically, the shell structure part is most nicely illustrated with maybe one of those two isotopes. So as I said before, if you have a nucleus and you want to steal one neutron from him, it's basically what is the energy to do that? And this is called the neutron separation energy and can be computed as a difference between binding energies of neighboring isotopes. So let's say if I take lead and take many isotopes of it, and then basically compute the so-called separation energy, you start to see that as you go neutron more rich, basically first here you have a shell at 126, and then as you go down, suddenly the neutron separation energy becomes zero, which means it's actually preferred for the nucleus to sort of start throwing neutrons out. But you can actually see that there's still some structure even below. Now, of course, those are the measurements, those are the predictions, not to fool ourselves. And the same is, of course, observed in different nuclei. Then, as I mentioned before, we have something called neutron skins. So you can imagine this as neutron skin is basically the difference between the radius of the protons in the nucleus and the neutrons in the nucleus. And in the normal nucleus, the, let's say, density distributions sort of overlap. And in the case of skin nucleus, you really have like a skin of neutrons around. And as we presented before the halo nucleus, we actually have like not sort of dense cloud around, but just a few of them circling around. So this is going to sort of show into density in the tail, not so much here in this overlap region. And again, for example, if we look at thin isotope, you can see that the sort of thickness of the neutron skin increases as we add neutrons to our isotope. And this isn't something that just theoretically predicted, but was actually in 98 measured at GSI. And there are many experiments at the moment that are actually trying to see where this phenomena is more prominent, because again, it's not completely clear why this kind of structure sort of appears in the nucleus itself. And let's say hopes are that this gives us more insight into what's going on. So the next thing which we have to look at is so-called exotic radioactivity, if we want, or basically what drives us back to the value of stability. There are normal physics courses which basically cover those three. Those two are sometimes mentioned, but this is basically, let's say, what was discovered before the World War II. Then later on, it turned out that there are many more nuclear reactions we have actually in the whole, how to call it, landscape. And it turns out that those reactions will actually appear as we go further away from the stability line, right? So basically, in some sense, you can say the exotic modes appear the further away we go from the stability. So as we approach so-called proton drip line and the neutron drip line. So this is, let's say, those two lines are, we'll get to the Ziga function later on. But basically, here is the limit sort of the landscape, and those are the processes that drive us back. So we're going to look at those later on, but I want to mention those three first. This is the so-called neutrino as double beta decay, which high energy physicists are very geeked about. And actually, it's recently they just published a paper that if there is decay like this, it's very, very long. I mean, it has very, very long decay constant. But those two, so the so-called two-photon decay and two-beta to neutrino decay, those two were already measured through very specific reactions. This one quite recently, and this one a few years ago. Double alpha decay and multiple radioactivity, which we'll show a little later, haven't been yet measured. So the first one is so-called proton radioactivity. So to make things clear, that's not the decay of the proton, but it basically means that the nucleus spits out a proton. And this has been predicted actually quite early in the 60s and then confirmed in the 80s in the lutetium 151, again at GSI. So you're going to notice through the talk that a lot of it was confirmed at GSI. That's not on purpose. We're not trying to push our results forward, but it's just, I don't know, we've been lucky. So the orange dots here in the chart are where this kind of processes occur and where they have been measured so far. So yes, you can see that this, let's say, proton radioactivity basically happens at the edge of the nuclear chart. And this is, in some sense, means that if you would remove one more neutron, so go even a bit more to here, the nucleus basically falls apart because the proton, how is it called, repulsion becomes too strong because there's not enough neutrons and the whole system falls apart. Then the next one is neutron radioactivity, which some people actually claim they observed, but they didn't, or depends how you interpret. So the issue is that you would actually need to have a neutron emission, but all the states that have been observed so far are more like resonances than actually isotopes, because they sure exist, but don't exist long enough that the neutron would actually circle around the nucleus at least once. So now if you take it that that's not the nucleus, then they haven't observed it, but if you say it's just a resonance, then they observed it. So now let's say we sort of mentioned what's on the limit of the nuclear landscape. But now how can we have stuff beyond the limit of the nuclear landscape? How can we have structure even there? And the answer to that is, as I said before, let's say, the coupling or the rotational parts become, so yeah, the centrifugal battery become important, very large English word. And what can actually then happen is that at the same time, the nucleus can actually emit two protons or two neutrons at the same time. And the interesting thing about this is that it actually allows us to sort of really see what is happening directly on the limits of where we know that the landscape actually exists. But of course, there might be actually something else beyond here, but we don't know that. To quickly explain what the two-proton radioactivity is, again, predicted in 60s, but already observed at GSI again in 45 iron. So the basic sort of, requirement is that the only process through which we can actually get two protons is directly to decay, so that the system decays directly into the ground state. And again, this has been observed in 2002. Then two neutron radioactivity has been actually observed pretty recently in 2010 and 2014. This, let's say, measurement has a nice trick that you basically use sort of the target to see if you had the bound state or not. So the idea is to wait that the decay happens actually outside of the target. So you produce your specific isotope that will decay in a specific way, and then wait for it to get out of the target and then decay. And then it basically means because it had to travel out of the target that it was sort of had its final lifetime. There are a few, let's say, more exotic modes, which are sort of weird, which are so-called beta delayed decays. So in beta decay, in some sense, we get a reaction involving proton or neutron. But what can actually happen is that basically, instead of, let's say, two proton emission, that sort of nucleus undergoes a beta decay and then also emits either a neutron proton or multiple neutrons or multiple protons. And again, this happens at the drip lines, so at the limits of the landscape. And this is because, in some sense, isotopes at the limits of the landscape are not as bound anymore, so this kind of reactions can happen. Right, this is again another set of processes, but it's sort of more of like going on and on. So the next one is double alpha decay that we're currently actually measuring at GSI. So the idea is that in a specific decay chain, the theory is predicted half a year ago that you should directly go from this isotopes, the so-called 2-alpha decay. So I think in July, we started the design of the experiment and then went online on 1st of January, so like in 4 months, with all the construction of ion optics and DSSDs and all of that, which is kind of amazing. But the basic idea with the measurement is that you use the stopping cell we have in Germany to install pretty radioactive thorium sources, then extract the thorium out and implant the products on a thin foil and then wait for back-to-back decay. And if this happens, we actually observe this kind of process. This remains to be seen, but at the moment they're doing the data analysis, so we might have some results soon, but we'll see in which direction. Okay, so there's a bunch of, let's say, features in the nucleus that we can measure and through which observe what's going on. And one of the, let's say, most interesting parts is that, for example, just through mass measurements, we can actually see many different properties depending on what the mass precision of our spectrometer is. But let's say the nuclei are just part of the picture in some sense, because they're not the only exotic states we have. And unfortunately, there are many more bound states. So the basic question is, if you look at the nuclear chart, it consists of 2 types of bound states, so protons and neutrons, and just 2 types of quarks, up and down. But as you know, we have more quarks. So the question is there anything else out there? And it actually turns out there's a lot of other stuff out there. I'm not going to even try to cover everything because it's too much. But the basic idea is that can we, through different types of bound states, gain new insights into the nuclear force? So if I try to give just a simple illustration, right? So if you look at the Bohr radius of an electron, the electron is going to be circling the whole thing pretty far out, and probably, if this were in scale, this would probably have to be somewhere there. But let's say the distance between the electron and the core is pretty big. Now, let's say you manage to capture a muon in the trajectory of the core, which, because it's heavier, significantly heavier, is going to circle around the core much closer, and it gives you a different kind of probe. And then the pion will be even closer to the core, and the proton and neutron, which we basically in some sense saw in the halo, will be very close to the core. And with this, we sort of get a new probe in what is going on in the core of the nucleus. Now, the first thing, and this again has been observed, I'm not making this up, are so-called muonic atoms. So in some sense, what you do, you take a beam of muons, shoot it into the stopper, and basically thermalize the muons. And you capture the muon by the gas and slowly transport it to the target. First, of course, okay, they jump to deuterium, but then deuterium transports it to the target. And now what happens is that this muon will sort of jump on a heavier element target, for example, curium or radium. And now you have a system which is, let's say, radioactive, but it has a muon circling around instead of an electron. And as a result, basically a lot of properties of the nucleus change, and the gamma spectra you're going to get out, the decay times, the transition rates, all of that was going to change. And again, if you can measure all of that, it gives you an enormous amount of new insight how things behave in the system. This has been actually measured. So the first muonic capture was done in 2002, and then now they're slowly going to more precise measurements. It actually turns out that through those 2 channels, you can actually measure some of the inconsistencies in the standard model. Don't ask me for details, but more here if anyone is interested. The second thing is so-called bionic atoms, which were again discovered at GSI. But for this, sort of the rest of the labs are kind of responsible. because the Japanese wanted to measure this, and GSI was the only lab that said, screw it, let's try it. And they installed the experiment in the hall, and in the first 15 minutes, they saw the resonance. And basically what happens is that you manage to get a state where a pion is circling around the core, and again, this gives specific properties. So the idea here is that you don't shoot pions into, let's say, lead, but you sort of produce a nuclear reaction in which the pion sort of is created and gets trapped around. Again, I'm not going to go into details of the physics of this, but basically, this is the reaction you look at. And then the last one, which is sort of the last class of exotic state, and sometimes one of I'm going to present, not the last that exists. But it's the idea is that can you flip one of the quarks in your whole nucleus, so U or D, into S? And there are reactions that allow this. One of them is, for example, impinging lithium beam on a carbon target, and you get so-called hydrogen with hyperon inside. So this is the kind of system where you have one up, down, and one strange quark. And this was actually an experiment that happened or was on the floor in March and in April, and now the data analysis has been ongoing and is very successful. And we'll see, maybe we saw some new stuff or we didn't. All right, that's it. Not everyone fell asleep. So we can't really close the story yet. There's a lot of stuff to be measured. But in principle, if we do measure some of those processes, we're going to gain a lot of new insight into what's going on in nuclear physics. Thanks.
Well, thanks, Ziga, for this very informative talk. So any questions from the audience?
Okay.
Then from the Zoom.
Yeah, go ahead.
Yes, Ziga, thanks for this nice introduction. Just wondered that when on page 25 or something, where you showed this plot of Carlos, what were the colors there? No, it's a little bit further back, I think.
Here?
The plot of Carlos on binding energy, Bertolani. Somewhere here.
But just give me a second. You mean?
Yeah, this one. Yeah.
This one. Okay, sorry. Yeah. Yes.
What are the colors?
Sorry. The colors are basically sort of variation of the model in some sense. It's all for the thin isotope, but different model parameters.
Okay. Thanks.
Yeah, you're right. I didn't mention this on purpose, but yeah, it's not clear from the top. Thanks. Anything else?
Any other questions? Well, then I may ask, what would you predict which exotic decays will be like actual in the future?
Measure.
Yes, yes. What would you bet on?
I mean, if the Japanese are fast in the analysis, hypernuclei and eta prime.
Okay.
Because this experiment was like really playbook.
Good.
Executed.
Good. Then looking forward to the next, or in 2 years, or in 3 years when results come.
Just to mention one more thing for the audience. So the problem with VASA is this is basically a small high energy physics spectrometer, and we literally have to take the whole machine apart. So this year, basically, the facility in Germany was blocked by 5 months just for that.
Yes, indeed. Well, yes. Well, one should mention when you presented these results that these results were performed by different international sub-collaborations. Yes. So and we are talking about exotic decay. So other labs, Ganil, Spes, Ganil, Legnaro, Riken, they also have fantastic results, but on some other physics topics. So here we are quite exotic, so there are not a lot of laboratories who can reach very exotic nuclei. So this should be mentioned. Yeah.
I mean, as I said in the beginning, the mentor was from GSI. So.
Exactly, and the mentor was from GSI. This is why it's tuned to the interest of the for its collaboration. Good.
Micha was first.
Yes.
It's okay. So it's easy to predict something where you cannot measure, but how many states were predicted in a region that you can measure and were not discovered? And if these are different theories that predict the same states, or it's a single theory?
Yes.
Yes.
Yeah. So this, what they did is they took different models and they sort of computed the highest probability weighted by different models that the nuclei should exist. And oops, it's not in this plot, but basically the region which the facilities, the ones that are right now getting online, should be able to measure is basically, let's say, somewhere around here. So there's still a lot of the nuclear charge region, which even if those facilities go online, we still cannot reach. Now, either because we don't know which nuclear reactions to do, or because the energies and let's say, the targets we're using are not correct.
Yes, also the reaction methods
Yes.
are, now the working force is like, at least for GSI's fragmentation, for super heavies, they have fusion. So it depends, but at one point, one has to think about the other reaction processes to reach certain nuclei.
Did I miss any of the part of the question? Or?
Yeah, no, so I wonder if you don't see this state.
Yes.
It's because you are unable to measure, and the theoreticians are confident that the state should exist, or it's okay, we have a problem with the model and we need to correct the model.
Well, it kind of goes hand in hand, because the issue is, let's maybe, I don't know, if let's go into the heavy region here. The problem is the models, of course, highly rely on what the data in that region is, right? So in some sense, as we measure this isotope, we can then predict better further, and we sort of have to go step by step. And I don't have this in this talk, but basically, let's say, where's the n equals that line displayed nicely? So here, for example, if let's say we go from here, the order of magnitude of the production of what we can produce in the lab sort of falls by one order of magnitude as we go to the left. So at the n equals that line, basically at the moment our machine can measure the, let's say, a process where we have at least 10 isotopes per hour. And if we go one more left, we are basically at 1 isotope per hour. I mean, we can do a measurement with 6 isotopes with enough statistical significance because the machines are good enough. But if you go to, let's say, 0.0 per hour, then, right? So it goes, it's not just reactions, it's not just theory, but it's really the interplay of basically machinery, detector physics, all of it. I mean, if it were easy, it would have been measured already. Matjaž, I think you were next.
Yes,
okay.
Samo vprašanje, kje je meja med tem, ko rečeš, to je bila samo ena rezonanca ali pa zelo kratko živo stanje, in kdaj lahko rečeš, da si potrdil obstoj izotopa? Je kakšna kvantitativna meja? Kako je s tem?
Should I answer in English? Or?
Yeah, so is there any quantitative measure, how you say, no, this was too short-lived? Is there some lifetime where you can confirm that then it's your additional point in this chart?
So there are two parts here. First, you can, as I shown here, if you compute so-called neutron separation energy, when the neutron separation energy is 0, there's the drip line. So the sort of the definition of the drip line isn't directly connected to the longevity of the state. But the resonance part, where's the resonance and where's actually isotope, it's not really clear. It's not really, the community doesn't agree on it, or at least I haven't found a definition, or the experts were not willing to point me towards one. But if you have an idea how to make a
Matei has an idea.
sure.
Yeah, let me try to answer Primoz. If you want to say that the nucleus exists, it has to last longer than the nuclear reaction itself with which it was produced. And that's sort of 10 to the minus 20, 10 to the minus 21 seconds. So you are basically thinking about that the nucleon has to circle at least once around the nucleus to be able to say something about this nucleus. And this is also connected to what you can measure. So if you can measure some properties of a nucleus, then it exists. If it decays as soon as it was created, then it doesn't exist. So that's sort of definition.
Well, I'd say it's a sort of definition. So, any more questions? Okay, then. Yeah.
Okay, if you go to another extreme, very long-lived states, you have a very good mass spectrometer part of your engagement. Can you scale excited states of the same nuclei with good resolution? Or
We can, the current, let's say, so when we were at the resolving power of 500,000, we could distinguish peaks that were up to 1 electron mass apart.
Mm-hmm.
So that was at 500,000. Now we're at 1.2 million. So I don't know how this scales, but I guess less than 1 electron mass. But it's also slightly, I mean, it depends on the isotope and also the production rates and the branching ratios and all of that, because it highly depends on the statistics and the analysis. But in principle, yeah. So that's the region, how much we can resolve. And of course, it also depends on the statistics, because if you have a rare isotope, then it's much harder to acquire and update.
So roughly, if it's excited state with more than 1 MeV energy difference, you in principle could scale it with mass spectrometry.
No, also half MeV.
Half MeV.
Yes, half or below even, but I'm not sure exactly how much lower than half MeV.
Okay.
But again, with current mass spectrometer we have in Germany, we're limited with the decay time, because we do so-called time of flight where we bounce, and then basically the longer we bounce, more resolving power we have, but
we're losing the
yes.
short. Okay. Thanks.
Well, Ziga, thanks a lot for your talk.
Thanks everyone for sticking with me for 40 minutes.
Thank you.